Check. Check, check, check. Check, check.
See. Yeah, no, this is. I gave all my talk there already, so. Yeah, sure. How are you doing? Hi, nice to see you.
Okay, so let's start. So welcome everyone to the ICTS String Seminar. So today we're happy to have David Bernstein, who will talk about BPS coherent state and localization. Over to you, David.
Okay, thank you.
Yes, it's on.
But they won't be here.
They're taking pictures from Zoom, right? Or yes, okay. So you should be okay. Okay, I might just not hear the questions if you ask them. Okay, so as some of you know, I'm one of the organizers of the current workshop going on at the ICTS. And then Rajesh came on Monday and told me, talk about some of your other stuff, the stuff that I cannot talk about there. So thank you, Rajesh, for giving me the opportunity. I have grants. The grants finance this, and they've told me that it's a good idea always to acknowledge them. So the stuff I'm going to tell you about today is supported by the Department of Energy in the US. I don't know if verbal acknowledgements are good enough, but I'm going to cross my fingers so when I put it in the form, I can click the check mark that says yes. Okay. So this story is about some gadgets that I usually go to, as they say, in my kitchen drawer when I have nothing else to do, which started its life as giant gravitons. So a giant graviton is a D-brane in ADS 5 crosses 5 or in some other geometries. They're a D-brane in ADS cross S. And if you do ADS CFT correspondence, then there's this idea that whatever can happen on this side can happen in the dual field theory. So the giant gravitons need to be dual to some interesting states. The giant gravitons are supersymmetric, so the states that the giant gravitons are dual to are supersymmetric. And supersymmetry is very nice in that it protects states from weak to strong coupling. And these D-branes in ADS cross S that are usually called giant gravitons preserve half of the supersymmetry. So basically, the full representation theory of this D-brane state in ADS cross S is controlled by these half PPS, half supersymmetric states in N equal 4 Yang-Mills or in the superconformal group. And they're completely determined by one number, which is kind of the dimension of the corresponding operator. And it turns out that there's not just one D-brane, there's a whole bunch of them, and they can all preserve the same amount of supersymmetry. So the number that is the dimension gets split into how many D-branes you have and various other sectors like that. But if you have a single D-brane, there's supposed to be one number. So it's dual to some interesting states in the conformal field theory, which satisfy that they preserve half of the supersymmetry. Okay? And if something is a D-brane, then D-branes are where strings end, so I can attach strings. So most of the work I'm going to be telling you about today is going to be on the side of just understanding these D-brane states better. And obviously, what I'm going to say is that there's some interesting states in the conformal field theory. And what I'm really going to do is I'm going to write a generating function. Of all these states. And the generating functions will be what I would call the BPS coherent states. Okay? So the idea is there's these gadgets. I have a generating function of coherent states. The particular generating function that I'm going to describe is some integral over some parameters with some matrices. So it has some free parameters and it has some integral. And it so happens that this generating function of all these states is going to be written as some matrix integral, and not path integral, but a matrix integral or a unitary matrix. And it will be this integral over the unitary matrix, which has localization. So the statement about localization over here is that I'm going to write this generating function in terms of an integral that can be written in terms of, that can be localized. And when you can localize things, what that really means is that there's critical points. And if you have critical points and you're in the right regime of physics, one critical point dominates and you can throw everything else away. And then this is the idea that once you have this critical point, you have a simplified set of calculations, which will actually let us get eventually, I hope, to not just attaching strings, but seeing how they interact. Right? One of the problems of the current approach up until recently that people use for these states is that the construction of these states is combinatorial. And the construction of states with strings attached to it is even harder combinatorics. And the computations that I would want to do eventually, which is kind of splitting and joining of strings, which is how do you get, let's say, the Dirac-Born inflow dynamics of the D-brane with all the fluctuations on it and how they interact. The splitting and joining of strings in this combinatorial, harder combinatorial becomes prohibitive. Yes? Right. So the idea is these states that are BPS coherent states and stuff is the starting point to add a whole bunch of things to take you away from supersymmetry in a controlled way with the extra information that the state you're starting with is very well behaved. Okay? Right. We're going to do everything in the CFT side. Yes. Okay. So the statement is, this is the physics in the bulk in ADS CFT. I have these D-brane states. I think I know what the effective field theory on a D-brane state is. It should be so many conformal Yang mills by however many D-branes I have on top of each other. And then there's going to be questions as to what happens when certain approximations break down, which is where we want to understand better what goes on. Okay, and then the idea is that eventually you want to do it in the conformal field theory side.
The CFT side at the point we
Right. So I need to explain to you how that is fixed in this generating function. So generating function has parameters. The parameters of the generating function put you in some place.
Okay. I mean, in principle, you can also break the supersymmetry partially, I suppose. I mean, the ground state is half SUSY, but you can have things with less SUSY, and probably you can consider non-trivial interactions.
So one of the...
Which you can compare with strong coupling.
Yeah, so...
That's in a way what Costello and others, I guess, and you probably are going to mention more.
Yeah, well, the thing is that once you get the gadget, you'll see that you can also do it for quarter BPS states at no extra cost.
Yeah, and some of the excited states can preserve, excited states about this can probably preserve quarter or 1/8.
Yes, but I want to go away from just preserving infinitesimally close to this. I can really go to more generic 1/4 BPS states. As in 2D branes that are giant gravitons in different places that preserve different supersymmetries and preserve a fraction of the supersymmetry. Yeah. And then starting in that one, so once I go to that one, that's a hard place to start in the combinatorial methods.
Right, right. No, I just wanted to address Subrat's point. I think that you can probably do some meaningful comparisons even away from this because there are a large class which are protected. And this is what this twisted holography people are. They have non-trivial OPs. And it's preserved by some supersymmetry, but it's not as trivial as half BPS.
Right. So I'm going to remind you a little bit about the supersymmetry algebra, just to put a little bit of emphasis on why these states are so simple over here. So the idea of the conformal group is that we have SO4, 2 superconformal group. That's the conformal group of ADS. There's an SO6 symmetry. And then when we split the SO4, 2 in terms of the global ADS characterization or the cylinder quantization of the conformal field theory, it's convenient usually to split this SO4, 2 into an SO4 and the SO2, so to speak. The SO2 is not really a compact SO2, it's a non-compact SO2. Sometimes people call that SO11. But the idea is that there is the splitting. The generator inside the SO2 part is what we usually call the dilatation operator. The SO4 is what we usually call rotations. And then these rotations commute with delta. So usually this is the way one does representation theory of the conformal group in the cylinder quantization. And then on top of that, there's this SO6 R symmetry, which I'm going to split into also an SO4 and an SO2. So usually there's going to be the R charge over here, and then there's going to be some SO4 R charge. And then there's going to be some additional generators that mix the SO4 and the SO2, which give you SO6. But I can talk about the Cartan of SO6 and talk about the three eigenvalues, R1, R2, R3. And then there's the generators of supersymmetry, which are going to have conformal weight 1/2. There's going to be the momentum, which is the one that has conformal weight 1. These act like raising operators, meaning that they add energy to the cylinder. And then there's lowering operators called S bar, and K. K is the one that's usually called the generator of special conformal transformations. These generator and P are closely related to each other on the cylinder. And then just like K is something that's related to P. So if I put this over here, This is a vector, this is a spinner. Then there's something in between P and K and between delta and K, which is analogous to Q, which is a kind of a mirror of it, and they're called special super conformal transformations. And then the idea is that these have dimension 0 in the dilatation. This has dimension 1/2. This has dimension 1. This has dimension -1/2. This has dimension -1. So usually when we say that a state is half BPS and you preserve half of the supersymmetries, what we really are talking about is not the full multiplet associated to preserving half of the supersymmetries, but the highest way state or the conformal primary associated to that multiplet. Okay, so what I want to tell you is what are the commutation relations of Q and S. Q and S, their anti-commutator, gives you something that has conformal weight 0, so it's a linear combination of delta, M, and dRs. The eigenvalues of M are usually what we call spin. And then these are the R charges. I flip which Q and which S I choose. I get different linear combinations of these gadgets. And sorry, a spin called J. And you really have to be careful. The M is SO4, so there's actually 2 spins in here. But the point is that you have a lot of these QSs. You can do the same with Q bar and S bar, and you keep track of Weyl indices. Here, if you do these 2 left-handed, then this is self-dual rotations, or the ones that are kind of M alpha beta, and then the other ones will give you the anti-self-dual rotations, which are the M alpha dot beta dot in the Lie algebra decomposition of SO4 into 2 copies of SU2. All of this is irrelevant in the sense that for the states that preserve half of the supersymmetries, something like this is true for Qs and Ss, and something like this is true for Q bars and S bars, and half of the Qs annihilate the state, and half of the Q bars annihilate the state. And if it's a primary, it's annihilated by all the lowering operators, which include SS bar and K. So when we say that something preserves half of the supersymmetries, what we really mean is that half of the raising operators in the Qs act by 0. And then these states are very special because there's a lot of anti-commutators where if you put here your state, this is equal to 0 because the anti-commutator of Q and S, if S acting on the state is 0 and Q acting on that state is 0, both of these will give 0. So what that means is that if you get this on the right-hand side, if this is 0 and the state is non-zero, then whatever linear combination you have here is equal to 0. And what can be shown in these happy PS states is that J and the analogous is 0, and R2 and R3 are 0, and only one of these R charges survives, which is the one that I'm kind of specializing over here. So there's no spin, and delta ends up being equal to the R charge. In some units, that one has to be careful sometimes. People have different conventions. So this is a convention for the SO6 quantum numbers, that the dimension is going to be equal to R, where it's this R1, which is this SO2. Okay.
These are the giant gravitons in the sphere, but
no, these are all the giant gravitons. They all preserve the same supersymmetries.
But aren't they the ones in ADS? But
they both the one on the sphere and on ADS preserve the same supersymmetries.
But the ones on in ADS, do they carry R charge?
Yes. The ones in ADS are some D branes that balloon up on the S3, and then you give them velocity on one of the circles of the SO6. And that's the thing that's necessary to actually give them an electric charge that lets them feel the self-dual magnetic field and get some electric, well, no, I said that wrong. That's what lets them acquire the R charge. Yes. Yeah, but they do have that.
Other way around, they carry, they are point-like in ADS, and they are,
yes,
but they are still rotating in.
Right. Those are the ones that are rotating on the sphere. You'd say, well, there's no electric charge to make them fixed, but remember that the flux is anti-self-dual. In the 5-form flux is self-dual, so there's flux in S and flux in ADS. In ADS, the D-branes are electrically, they feel an electric force. That's what kind of keeps them from collapsing. And in the sphere, there's a magnetic field on the S. And because these things are rotating on the sphere, there's magnetic forces that act to prevent them from collapsing to zero size. So in one case, in the ADS, they're balanced by electric forces, and in the other one, they're balanced by magnetic forces. Again, the statement here is, all I want to tell you is that this is the motivation. This is the supersymmetry algebra. And then I need to look for states that have delta equal R, that have zero spin, and that have all these R charges equal to zero. Okay. And then I can look at the field content of N equal 4 Yang-Mills. And then
I have a question. So can the D-branes are the D-branes of codimension 1?
Okay, so the giant graviton D-branes are D3 branes. There are 3 spheres inside either ADS or the S5.
Yeah, so that's what I wanted.
So there are D3 branes in the full 10-dimensional theory. Okay, so as I said, I'm going straight to field theory. So I want to find states that have delta equal R. So if I look at the field content of N equal 4 Yang-Mills, I want to split it according to these dimensions and this SO6 representation. So if I'm sending out an SO2 inside SO6, I can have the positively charged under the SO2 and the negatively charged under the SO2. For the scalars, there's going to be one that is positively charged, one that is negatively charged. There's usually some complex combination fields. And then I'm going to have some Y1, 2, 3, 4, which are the SO4 order vectors. Okay? And these one carries are one charge. This one carries anti-R charge, and this carries zero R charge. And then there's also the photon, which has R charge equal to 0, but it can have spin. And then there's the fermions. And the fermions can carry plus or minus 1/2 in R charge, but their dimension is 3/2. Okay? So the idea is if you start with states in ADS cross S, you need states in the field theory that have this condition that the delta is equal to the R charge. And then I can describe states in a conformal field theory, either as states on the cylinder or via the operator state correspondence as insertions of operators in the origin. So when you look at operators, you have these mu, psi bar, z bar, y1, 2, 3, 4. And you're looking for states where the dimension is equal to the R charge. And then the other ingredient that we usually have is covariant derivatives, which also have 0 to the R charge, but they have dimension 1. So if you look at all of this table, which one has the dimension equal to the R charge, this is the only object that we get. Everything else, the dimension is bigger than the R charge. So if I write a word and I want it to be half BPS, it's only made out of the Z. Okay, so what is Z? Z is in the adjoint. So it has some ij. And then you can ask, how can I make something out of z's that is gauge invariant? And then you say, okay, if it's only z's, I take products of traces e to the n and sum over all of these things. So I take it to the n1, to the alpha 1. And I just have powers of these objects and I do the most general combination. And if you're doing gauge theory with SUN or UN gauge theory, there will be a slight difference on whether the trace of Z is allowed or not. Because in SUN, the trace of Z is not allowed, and in UN it is. Since I want to do large N, I'm going to ignore that. It's easier to do things with UN than with SUN, so I'm going to stick with UN. Okay. So the idea is that this is the general combination, and then under the operator state correspondence, inserting Z at the origin ends up being equivalent to, if you do things on the free field theory on the cylinder, it's equivalent to taking the raising operator of the Z operator in the S wave. Because you need to have zero angular momentum, and you need to have the same R charge over here. So I can talk about these gadgets either in the operator language where I take these traces, or I can go and write them in terms of the raising and lowering operators on the theory. And these will be inserted at some cylinder time equal to 0. So I'm going to do physics over here. Okay, these states have BPS, they are states, and then the nice thing about supersymmetry is that it tells you that these states are protected from weak to strong coupling, and that actually nothing happens to them. And moreover, the non-normalization theorems tell you that any calculation that you do a strong coupling that is just about this state and not, nothing too fancy, is exactly protected by supersymmetry, so you can do it at zero coupling, except for gauge invariance, and you will get the right answer. So in particular, the norm of these states can be computed in free field theory, and that's one of the things that is protected. So if you, let's say, diagonalize these states or talk about the Hilbert space of these objects, you can do it at zero coupling. So all of these analyses is to tell you that something that I want to understand in ADS cross S can be described exactly by zero coupling physics if I do this carefully. So if I preserve the supersymmetry, nothing happens. And then this is a good starting point. So if these objects preserve the supersymmetry and they're protected, if I add some small breakings of supersymmetry, the small breaking might be computed like an anomalous dimension or something like that. And if it's sufficiently small, I might be able to extrapolate it. Or if there's some other techniques, I might be able to extrapolate it. So the idea is to start this way. Okay, so all of these analyses is to tell you that at the end of the day, I've reduced the problem of n equal 4 Yang-Mills with all of the complications of a field theory to the problem of n squared harmonic oscillators with a Gauss's law constraint. And the nice thing about these representations that preserve half of the supersymmetries is that they cannot be lifted by mixing with another multiplet. And the reason for that is that the multiplet that they would mix with to make them massive has a negative norm state, so it cannot be realized in a Hilbert space. So even though in principle you could imagine that these things could be lifted by having some other representation come in, that representation would have some negative norm state, and therefore it's not allowed to attach to this object in a Hilbert space with a positive definite inner product. And the important thing about the cylinder is that Q is the adjoint of S. So when we do this thing, this is actually a positive operator. So this is not only equal to this combination, but it's also greater than or equal to 0 for all possible combinations. And this is what tells you that The dimension is usually bounded below by some linear combination of the R charges plus the spins. So if you want to have something of low dimension, it needs to have low spin. Okay, this is all standard conformal field theory representation. So I've taken care of the first part, which is telling you what the states are. Now I'm going to erase the conformal group structure. And I've told you that I reduced everything to some generators. And because these things had adjoint indices, they need to have matrix indices over here as well. Okay, so all of this is to tell you that I'm going to do quantum mechanics with free oscillators and squared free oscillators. Okay.
Question.
Yes.
So these Z's also have a position space-time dependence as well, right?
I'm doing it on the cylinder, and the space dependence is that they're uniform on the cylinder. So I can reduce the problem to zero-dimensional
Okay.
quantum mechanics as opposed to field theory. Okay. Okay, so now the next step is to write a nice generating function of things with the harmonic oscillators. So let's first do it for a single harmonic oscillator. If you have a single harmonic oscillator, we know that there's a ground state which is annihilated by the lowering operator, and you can define the end state as a dagger to the n acting on the ground state. Okay. So what is the generating function of these states? It will be some function of some parameter lambda, which will be some type of n, some lambda to the n, and then there will be some alpha n. So the most general generating series would be some type of description like this. The one that is most convenient to use is f of lambda equal to exponential to the lambda times a dagger on 0. Okay. This is a generating function of states. I picked one. If you've done quantum mechanics in undergraduate quantum mechanics and you ever heard about coherent states, these are coherent states. So there's 2 points of view about this object. If lambda is a formal parameter, this is a generating series of all the states. This is the one what the exponential gives. And if you think of lambda as a formal parameter, you can use this gadget to manipulate expressions and use calculations, and then this encodes all the states. So you can do calculations not in one state, but in many of them at the same time. The other point of view is that lambda is a proper number, and this state is a real state. And when that happens, this lambda is something that describes semi-classical states. And these are states that satisfy the, that minimize the uncertainty principle, that they saturate the momentum position uncertainty relation. And on top of that, they happen to be eigenstates of the lowering operators. Okay. This is very good. And then you can recover from these generating series. What?
This description in terms of harmonic oscillators,
yes,
it's probably good for counting, but do you expect that this semi-classical description is valid at strong coupling? When
yes.
I mean, why do you expect?
This is the non-normalization theorem that for these free fields, they go from weak to strong coupling with the Hilbert space norm not being affected. So the sum logic of norm of these states doesn't get perturbative corrections. This is one of the claims in the literature.
That's because the only thing one is looking at is counting. Not affected. Once you orthogonalize the states, this means orthogonal states to orthogonal states.
No, counting of states does not mean that the Hilbert space norm inner product of the states is not, but the basis is not getting deformed as you go along, and the inner product is getting deformed into some more generic Hermitian product of things that, but there's not just one state at each energy, there's a family of states at each energy. So it could be that what we call the metric of the states could be deformed as you go from weak to strong coupling. The counting stays the same, but what I want to do is physics. So physics really means that I'm going beyond counting and I'm really wanting to compute matrix or operators or matrix elements of proper states and compute, dimensions and anomalous stuff and attach them and find a good starting point for computations that let me do computations in ADS cross S. So I want to do calculations of weak coupling that I can extrapolate to strong coupling without just having to implicitly follow this thing, but where I know exactly what state I'm really supposed to match. Yes. Okay, so
question. Eventually, you are going to break the supersymmetry, right?
Eventually, we will. At this stage, I'm telling you how to do the harmonic oscillator. And I'm going to tell you that this function encodes something very interesting when you actually compute the norm of f of lambda squared. So if I do f star of lambda star times f of lambda, where this is the dual generating function with some dual parameter, which I'm going to call lambda star. Eventually, lambda star is going to be the complex conjugate of lambda, but never mind that. If I do this overlap, this calculation is going to be written as the vacuum expectation value of e to the lambda a dagger ground state e to minus or e to plus lambda star a. Okay, I'm going to tell you what the magic is. The magic is that you can compute these by using the Baker-Campbell-Hausdorff formula, and what you get here is 0 e to the lambda star, e to the lambda a dagger, e to the lambda star a, acting on 0. And then this is annihilated by this one, 0 is annihilated by this one, and this is e to the lambda star. All right, so by doing this inner product, the first thing that I realize is that this exponential is absolutely convergent for any value of lambda star. So f of lambda actually defines a state. If lambda star is the conjugate of lambda, that defines the adjoint. So this is less than infinity when lambda star is the conjugate of lambda for any lambda. So this is a state for any value of the lambda parameter. So there's no restriction on the lambda. This is not an asymptotic series. This is actually series with an infinite radius of convergence. The second part that's important is that when you look at this and you compare with this one, you can also do the overlap in this form, and you would get m sum of lambda star to the m, sorry. Lambda to the n over n factorial, and then this would usually be the sum of lambda star to the m, lambda to the n, overlap of m and n, divided by m factorial. So I can compare this double series with this series over here. And then I see that in this series, only when n is equal to n, I get a non-zero answer. So that means that these m and n need to be orthogonal to each other. So I find that m times n is delta mn. And then you compare coefficients. This is 1 over n factorial. This is 1 over n factorial squared. So the thing in the numerator needs to cancel one of the denominators, and then you get an n factorial, and this n factorial is the denominator. So this generating series, when I do overlaps, automatically encodes all the norms of the states, and this is a non-orthonormal basis. It is orthogonal, and then we're good. Okay, so I did this for one harmonic oscillator. Now I have n squared harmonic oscillators, so I'm going to play the same game n squared times. And I'm just going to do the same game. So I'm going to introduce more generally a generating function which will do exactly that, which is basically I pick a matrix and then I do exponential to the trace of the matrix times a dagger. So I don't have to write matrix indices acting on the ground state. So this is a harmonic oscillator n squared times. This is still a coherent state in the sense that it's an eigenstate of the lowering operators. When I act with my favorite gauge invariant state, like trace of a to the n, acting on this state, I get a trace of lambda to the n acting on this lambda. So this looks nice from the point of view of having an eigenstate of my single traces, and these are the things that usually get matched to single particles or on the alias dual side. So these will also be coherent states in the sense that they're eigenstates of the corresponding gadgets in the dual supergravity theory. So these are candidates for coherent states in gravity. So one of the things that I'm trying to tell you is that just because Enikoff-Yang-Mills and supergravity seem to be completely different, there's this usual statement that classical in one is very quantum on the other one. Here you find a class of states which are kind of classical on the field theory and that are classical in gravity. Okay? So it doesn't need to be true that it's always quantum to, that classical always maps to quantum. You can have something classical mapped to something classical. Okay. There's a problem with this. The problem is not computing the norms. The norms are straightforward. I can compute the norms of any of two of these coherent states, and I'll get some generalization of this exponential. I'll get some, where do I have this? This will be replaced by exponential of trace of lambda star lambda when I do it, and you can follow the indices into that. That's not the problem. The big problem with these states is that they are not gauge invariant. Right, I just took some random n squared matrices and I told you that what I needed to do was really match to gauge invariant states. Okay, so the naive guess to start is that I can do computations, but what I got, the gadget I got, is not well behaved because it's not gauge invariant, so I need to do something to it to make it gauge invariant. Okay, so what I can do is take this object and project it into gauge invariant states. Okay, so I started with something that was nice for computations, and I'm going to introduce a projector to make it gauge invariant. And this is the gadget that will do all the heavy lifting. So we already did half of the heavy lifting, which is have nice computations for field contractions. The next part will be project onto gauge invariant states. Okay, so let's do that. Yeah, I couldn't. Yes.
The gauge transformation property of your oscillators.
Yes, so it has to be gauge invariant under UN conjugations of the oscillators. Yes, under the adjoint. The A's are in the adjoint. So I'm going to tell you how to do that. Okay, so I'm going to define a new f of lambda, which is gauge invariant. And then the way I'm going to do it is I'm going to average over the group action on the A dagger. So I'm going to take 1 over the volume of UN, the integral for U of the conjugation of A dagger because I'm averaging over the groups. This is guaranteed to be gauge invariant. Okay. It's the usual trick that we have something that's charged under a symmetry and you want to find the one that is uncharged, you average over the symmetry. And this is the way we usually do it for discrete groups, but it also works for compact continuous groups. Okay. And then you can do the computations like I was doing before of f of lambda star. I'm going to call this a star product times f of lambda, which is this norm. So what do I get when I do it? I'm going to have 1 over the volume of UN squared. I'm going to get an integral over U, an integral over V, and then I contract the raising and lowering operators by the usual with contraction, that we call it. And then I get exponential to the trace of lambda U V lambda star V dagger U dagger. It doesn't matter if I use V or V dagger over here because the measure is invariant under that change. So if I screw up on the calculation, it's okay. And the point is that I got rid of the quantum mechanics and I just got a number. Okay.
Question. So when you transform the lambdas by the unitary transformation, shouldn't the A's also transform in the same way?
No, I mean, this is really a transformation of A dagger. I can hide it inside lambda if I want to. But the point is that the stuff that is invariant when I do conjugations of under U is the eigenvalues of lambda. So this will really only depend on the eigenvalues of lambda. So in the end, I can gauge fix lambda to be diagonal. So it's common to gauge fix this to be diagonal.
Why is trace lambda A gauge non-invariant? Because it's a trace.
This one over here is an operator. Okay? And you can think of it as conjugating lambda, and the thing that is invariant under conjugations of lambda is the eigenvalues of lambda. The point is that you can think of U as acting on A dagger or on lambda. Once you have it started as acting on A dagger, but I can kind of sneak it into lambda, so I can make lambda be diagonal. And in this formula, because I already got all the contractions, I got rid of the A's. There's nothing charged under the original gauge group any longer. This is just an integral over these auxiliary U and V variables. And what you see here is you get the product of UV and its inverse. So it's convenient to pass to a composite variable called DUV. And because of the hard measure being group invariant, I can kind of put it inside here or outside. This basically becomes an integral over U tilde, U dagger tilde, where this is U tilde. And then you see that one of the integrals is doing nothing, so I can cancel one of these gadgets around. And I reduce the problem to a single group integral. And U dagger is the same thing as U inverse. Okay, so this is my answer. So my answer is, after doing these computations, I boiled down the problem to a matrix integral, and this matrix integral computes the overlap of these coherent states. Okay. This is a famous integral. And one of the buildings here is named after one of the people who invented this integral. This is so-called the Harish-Chandra Itzkison. Oh, I hope I got this right. I think it's written like this, Zubair integral. Okay. I know, that's exactly what I meant. Let me tell you why Harish-Chandra was doing this. He was studying harmonic analysis on group manifolds. And then this object over here showed up as some form of heat equation on that, and then you can extract from here all the information about harmonic analysis on the group manifolds. So this gadget that showed up here, this averaging over U, is the idea that you can go from the group to the Cartan. So instead of working with the full group, representations and everything else are determined by the Cartan. So if you can kind of make your way to the Cartan, there's a reduction of the full group to the Cartan, and then you can do harmonic analysis on the Cartan, which is a simpler space than the full group. Okay, this is why Harish and Chandra were doing this integral. Itzkison and Zubair were doing it for different reasons. But the punchline is that this is a number that is actually well known. So I'm going to describe the answer. The solution, if the lambdas are diagonal, I can think of lambda as a set of eigenvalues and lambda star as lambda 1 star and star. The answer that you get from here is that this thing over here is the determinant of e to the lambda I, lambda j star, and then there's some things that show up in the denominator, which is the Vandermonde of the lambdas and the Vandermonde of the lambda stars. Okay. So Itzkison and Zubair conjectured that this was the answer, and then they proved it by using a character expansion. Okay. Let me give you a different interpretation. For each term in the determinant, this is a sum of exponentials. So this looks like an exponential of an action divided by some which depends on a permutation because you're doing the ij and determinants is sum of all permutations. So it depends on a permutation signal. And when you see something like this suggests that there's some localization formula, that these are critical points and these are the determinants that show up. And this is exactly what happens. And the people who proved this was Duisterman and Heckman by geometric localization. Geometric localization is that if you have a symplectic manifold and you do the integral over the symplectic manifold of a moment map, then it reduces to a fixed point of the moment map. And then you should complain because I'm doing an integral over U. U is a group manifold. Group manifolds are not symplectic manifolds. So what happened here is that U is really acting by conjugation. So if you think of lambda as being diagonal, there's a subgroup of U which commutes with lambda that does nothing. So what you should really be integrating is over that Coset space, which is U tilde modulo U1 to the n. Okay? This is one of these classifying space for representations. This is a symplectic manifold. And it's this complex manifold with this coset where the localization argument actually works. So this is kind of equivalent localization that we have to divide by this. But you know, the point is that this is a very famous integral, and then you get this exact sum over saddles. Okay? And now, this is what computes overlaps between any lambda and any lambda star. So I can actually choose lambda star to be the conjugate of lambda. And then when you look at these expressions over here, you see that you're dotting the vector of eigenvalues of lambda with the conjugate of the eigenvalues of lambda with some permutation. And then the Cauchy-Schwarz inequality tells you that when these two vectors are aligned, that's when you actually get maximal overlap. That you permute these eigenvalues and do some other stuff, the norm of what you get is going to be smaller than the one that you get from when they're equal. So the statement is that this full computation can be approximated in the right regime by, instead of determinant, is e to the trace of lambda bar, lambda divided by delta lambda bar. Okay. This is a statement about a saddle, and then a lot of the physics is, if the saddle dominates, you can go further. So if this is a very dominant saddle, then you can throw away all this stuff. On the other hand, this was an exact answer. And when I built these states, I started from coherent states, which I told you were generating series of all possible states. If I have all possible states and I project them onto gauge invariant states, this is a formal sum over all the gauge invariant states because you had everything before and you project the stuff that's left over by gauge invariance. So you still have everything that's under gauge invariant states. And then, there was this proof that I told you about of how people show this formula, which goes by character expansions. This formula over here can be written as a sum over characters of representations of SUN times the character bar of a representation of XUN with some denominator D of R. Okay, so the punchline is that the R is the same as this one. Actually, these are called Schur functions. So the Schur function here is equal to this one. The same argument that I use in the harmonic oscillator to show that states were orthogonal says that because these things show up paired with the same R and R prime are different. When R and R prime are different from each other, don't have an overlap. And what you have to remember is that this expression is of the same type as this expression. And if I have a character expansion that's well defined, even if this is an operator, it's a polynomial on the traces of this gadget. So this is something that's well defined as an operator. So you can basically write the same structure with characters of lambda, characters of a dagger, and do the overlaps. And then what you find is that the character states are orthogonal to each other, and the norm of these states is this denominator. Okay. So this one-line argument-ish bypasses this brute force combinatorial way of computing the norms of these states that was done originally by Cordy, Janicki, and Anguilla. So this contains everything. It contains all the combinatorics. And the point that I want to emphasize is that generating series are smart ways to do contractions and combinatorics. So if you have the right generating series, it bypasses the hard part of doing brute force combinatorics. Okay, how am I doing here? 12:30. How much more time do I get? Okay. So this is the part where there's two ideas. One is that we had an exact formula. It has a lot of fancy, nice math that is very well known. And then there's the idea that there is an approximation to the dominant saddle that can be very useful in real computations of all the stuff.
So again, going back to the branes and ADS versus the sphere. So there are these, semi-classically, you think of these determinant operators or subdeterminant operators.
Right. This is a different expansion.
Yeah, so this Schur expansion is another way to, the Schur gives an orthonormal basis of operators, but which are the ones, so is it that some of the representations, some class of representations correspond to the sphere?
Yes.
Some class correspond to the ADS?
When the representation R is mostly antisymmetric, these are the ones that correspond to ADS because you have a floor and they cannot have more than n boxes, so they have a maximum energy, these are the ones that are giants on the sphere. Because there's a maximal giant, which is a diameter sphere.
Whereas the long ones can be anything arbitrary.
And the long ones can be anything arbitrary, and these are the ones that show up in this expression. Now, when you make one of the eigenvalues large,
can I ask a question?
You end up in this one. Yes.
When you are projecting the states which are not gauge invariant on the CFT side into gauge invariant states, so
yes,
what is that translated into the gravity dual?
So the point is that all the states of ADS correspond to gauge invariant states. So the other states are not physical. So the correspondence requires that you pick gauge invariant states. Gauge variant states are not allowed in the ADS CFT. Okay, so I'm going to cheat a little bit. I'm going to tell you two things. One that I'm doing right now, and I'm going to tell you that this is not the only way to go. There's other ways to do calculations. So there was this higher standard way of doing things. I integrated over some U, and think of these as an auxiliary variable that I introduced to make my life easy, and then I introduced it. There's all the generating functions of gauge invariant states. Rajesh was mentioning one. You can take the determinant of lambda minus a dagger. All of these are gauge invariant. And then this is another generating series that showed up, and I wrote about 10, 15 years ago, and I spent a huge amount of time writing this generating series and trying to do calculations directly with that generating series. And then something really, really important passed me by. That's the determinants of Grassmann integrals. So you can also write this as an integral or a vector of e to the psi bar lambda minus a dagger. Okay, so many years ago, I wrote papers with these gadgets, and I was attaching strings to these gadgets, trying to do all kinds of fancy math with this gadget. That's completely equivalent to starting with this gadget over here. And if I do an overlap, then I go from 2 fermions to 4 fermions, because they'll also show up something in the dual state. When I do an overlap, lambda bar lambda, in this case, I end up with an integral over psi bar psi tilde bar psi tilde, and then I do the contractions of the A daggers. I get an e to the psi bar lambda psi plus psi tilde bar lambda bar psi tilde, and then there's the overlap of these two, and then I have to contract them carefully, and I get some minus sign, I think, from Fermi statistics and some changes that one has to do. And I think I get minus psi bar tilde psi dotted with psi bar psi tilde. Okay. It's a computation. These are vectors. You get this dot product times this dot product. And then this can also be saddled in the sense that there's the Hubbard-Stratonovich trick that one can use to eliminate this quartic term in the fermions and replace it by a Gaussian integral. So this integral, this sigma bar, and this is over a single variable. And now I get this integral of fermions to the 4th power. And then I get here an e to psi bar lambda psi plus psi tilde bar lambda bar psi tilde. And then I associate this one to sigma psi, and then this one to psi bar. And then there's some factors of I that I forget. Never mind that. But you do get a minus sigma bar. This is the Hubbard-Stratonovich trick. And then you've made the integral over the fermions quadratic, and this is a determinant. There's going to be a determinant which is roughly lambda star. And then there's a sigma and a sigma bar, and I think there's some factors of I forgot over here. And then this is to the nth power, which is the n of the number of colors, okay? So I can compute this overlap as a integral with a Gaussian, some determinant, that's the calculation, okay? And then if you expand these, sorry, lambda bar. And then if you do this carefully, what you really get is lambda bar plus sigma bar to the n. That's what this 2 by 2 determinant is. And then you can actually tailor a method of orthogonality of the various pieces. Some things that involve gamma functions, right? Sigma bar to some power, e to minus sigma bar, and it's gamma functions. And you can recover all of the physics, but just like before, you can also do a saddle of this integral, and the saddle will dominate. That's the thing that lets you do an improvement. And I can do this now with more than one determinant, so I can have a determinant when this matrix is not 1 by 1. But where I do this and I take a product of determinants, and I play the same game, and then the Hubbard-Strassanovich trick will be more complicated. But the idea is that the saddle will be sigma bar more or less diagonal. And this is where the advantage comes in. If I have these fermions over here, these fermions transform, this is gauge invariant, because in some sense, the fermions transform in the fundamental. So just like I could associate lambda to the adjoint, these are the fundamental. This is also a generating series that is very useful, and this is the one that we would use for the sphere giants, okay? So the idea is that how do I attach an open string? Well, I attach an open string by adding a psi tilde and a psi and some other word of the field theory, okay? So if large n works well, this is a small correction to the saddle that I got over here already. And therefore, once I go into this sigma representation, I'm going to be computing this psi tilde overlap around the saddle, and then it'll be some Green's function or some, inverse. Okay, so now I'm going beyond half BPS states. And then I'm saying I want to decorate the state with something where I attach the word of my favorite n=4 Yang-Mills word, and I pair it at the endpoints. So this is in the adjoint, I pair it at the endpoints with the psi's. And if I pretend that psi transforms in the fundamental, then this is UN invariant, okay? And therefore this is gauge invariant. Right, this one on the side was acting on the vacuum, but now I want to pass to something extra where I take the same expression over here and I take my favorite word and I act on the vacuum. Right, yes, but the point is that this is a word with ends and the ends are attached to these fermions. So this looks exactly like open strings attached to d-branes. And if I have more than one of these eigenvalues over here, I have more than one of these fermions, I can stretch words between different eigenvalues. And then there's some hidden U1 symmetry to the n, to the k over here, where you have k eigenvalues, that tells you that you're only allowed to do it if they are going to form closed loops in some graph that they have some charge equal to 0. Okay, so the bulk interpretation is that you have a giant graviton. The position will be parameterized by lambda. So which giant graviton it is will be characterized by lambda. Lambda goes from being a formal parameter to a real number. Just like when you go from a coherent states as a formal sum, you can also go to real numbers and get an exact state. So we replace the lambda by a real number, and then the saddle depends on lambda. And then on that saddle, with some real value of lambda, you can add this stuff. And then because it's a word with endpoints, and the endpoints are attached to this gadget over here, This gadget is interpreted as a D-brain, and this is interpreted as an open string attached to D-brain.
But this is the description, right? I mean, this is, you know, all these questions you had about CPK.
Yes. Right. Okay, so this is a description that is nice. And then what the next step is, let's do anomalous dimension computations. And then this induces a boundary condition on the spin chain, and this can be understood, and this was understood many years ago. And the idea is that this lets us do the boundary conditions more systematically than before. In this determinant, it is a number. In this one, it is a UN matrix, and the eigenvalues will really tell you how the field theory is configured in the Coulomb branch, more or less. So the eigenvalue, if you have one large eigenvalue and the other ones are zero, you have the ground state, and you separated one eigenvalue in the bulk, and then you can relate the coordinate of that eigenvalue to the rest of them. And then you have an exact formula for the product, or for the overlap.
Yes,
but if eigenvalues are zero, you get into trouble.
When you compare the anomalous dimensions, it will be for BPS operators or non-BPS?
No, these can be non-BPS operators. But you can do planar diagrams over here, plus whatever gets induced from the boundaries. The boundaries also induce additional corrections. And these will provide, let's say, a spin chain with boundary conditions. And as I said, this was worked combinatorially a long time ago. So this is another way of generating the same combinatorics for cheap. And because you have a good saddle, a lot of the calculations that were hard before are less hard now. The new advantage of this stuff is that you can now think, well, what does the generator of dilatations do? It can also bring powers of psi bar and psi when you're acting on this object over here. So we'll start telling you about splitting and joining in terms of these auxiliary fermion variables. So you can actually compute anomalous dimensions, including non-planar corrections, that will actually tell you a little bit about splitting and joining of strings. And this is a lot nicer to do than brute force combinatorics in the original files. So this part we haven't done. So what I'm telling you is that the integral didn't have to be over U. I could do it over fermions. Fermions kind of have the opposite statistics of U. So beforehand, here you were pairing things in a way that you were comparing the eigenvalues of lambda to A. If you do things with fermions, the fermions kind of change the notion of eigenvalue to some kind of dual eigenvalue or some other stuff like that. If with this one you generate mostly rows with some large eigenvalue, in this one you're generating rows. So it kind of switches rows by columns in some form. Yes. So this statement was starting at G coupling equal to 0. And I told you that for the half BPS states, G equal to 0 is the same as any coupling. No, the anomalous dimension will eventually start depending on lambda. This is a state, and then when you compute anomalous dimensions, the parameter of lambda sneaks into the computations because the saddle knows about where lambda is. Well, there's a little bit of a trick because you have to worry also about the normalization of the psi. So psi tilde psi gives 1, but psi with the words doesn't, right? Psi tilde psi is equal to 1 in some sense. Psi tilde psi is really the sigma parameters, and the sigma has some value. And this goes like n. So you have to be careful with the n counting.
Either the anomalous dimension is order 1 or it's order 1 over n.
Okay, so in this calculation, the anomalous dimension is of order of G-Youngman squared times n, including the boundary conditions plus corrections 1 over n on top of this stuff. This is when you actually go and say, this is my starting point at 0 coupling with the word, and then I can compute the dilatation operator acting on that object. And because I have a nice little large N gadget over here, which is the introduction of these additional auxiliary fermions, I can do planar counting, which has additional worldsheets, which involve the fermions psi running in loops and doing stuff that help with large N counting. No, there's no GEMS on the fermion integral. The GEMS will show up because when you act with the dilatation operator, you act with derivatives with respect to A, and that will bring down powers of psi till the psi. And then the powers of psi till the psi, those contractions carry powers of n. So you get a GEMS squared, and then you get powers of n from the fermions, so you get order GEMS squared times n. So the combinatorial addition of what happens on the boundary carries also power of n that makes it comparable to what you will compute in the interior of the word. So what you get is a spin chain with boundary conditions, and the boundary conditions kind of scale nicely.
Yeah, I mean, in the original Yang-Mills theory, if you didn't do it in this way, you would have had the words, and the words would have had contractions, and those would get anomalous dimensions. So I think this is mimicking that, because when you introduce the dilatation operator, if you compute the expectation value of the dilatation operator, then as we said, you will be bringing, because the dilatation operator now has additional correction.
So the dilatation operator is roughly the commutator of lowering operators, A times A dagger. This is a way to think about it.
Yeah, this has a DG Yang-Mills.
Yes, so and then there's a G Yang-Mills squared. And then the A brings down powers of these fermions. So you're formally changing the number of words. But some of these words are, psi to the psi with nothing inside them. So they're kind of trivial words. And in this saddle, they evaluate to a single number. So it's easy to compute what those corrections are. And then those give you additional contributions. But if you split and join words, if you act with one A here and one A here, and you bring it down here, you go from two psis with words in the center. So you can start splitting and joining these strings systematically. This is the new thing. But beforehand, we couldn't do it systematically. Now we think we can, but the computations are a little bit of a mouthful, but we can.
Functional integral computations, not combinatorial.
Okay. Now the other problem here is that it's annoying to have n eigenvalues. I want one eigenvalue. So I'm going to give you a third matrix integral.
Sorry, so this notation, you use lambda in both, but
right. The idea is that there's a parameter. There are different parameters.
There's no limit in which this lambda agrees with.
No. Here I'm using lambda as formal parameters. This was a number, and this was a n by n matrix with n eigenvalues.
Determinant just gives you the rows.
Right.
The column kind of.
If it's a single determinant, if I have multiple determinants, then I can get many giants and do this stuff. And then, that's what I tried to do many years ago, and I gave up because the computations were horrible. Because I didn't have the saddle of these, extra bosonic parameters on hand. Okay, I'm going to do a final calculation.
Can't you do that word computation in this first picture?
Yes, but so let me tell you what that looks like. So the lambda i's is lambda 1 up to lambda n. And you can think that these are matrix, and then there's vectors associated to the eigenvalues, which are the eigenvectors of lambda acting on these objects over here. So what I need to do is I need to decorate the words that I would have over here with vectors. And this would connect something between eigenvalue I and eigenvalue j. But then you notice that this is not gauge invariant, so I need to stick in a compensating u dagger and u, because you can think also of u as something that tells you how the eigenvalues of lambda get attached to these objects. So the eigenvectors are kind of like a square root of this gadget, and you have the eigenvector times u. So there's a way to attach open strings by taking the eigenvectors of lambda, putting it on the ends, and putting the u's in the center, and then doing the integrals with correlation functions of u inside traces. So if you want to compute things, you're going to get correlators or matrix models of this integral over u, which in the saddle point approximation, after I introduce the lambda bar, I'm going to pick my dominant saddle and do those computations there. But the point is that this is annoying because you need to keep track of n eigenvalues all along. And then there's these denominators. If you want to central all these eigenvalues to 0, this thing is not going to look that pretty. Even though the answer is regular, there has to be some horrible cancellations. So what I'm going to do right now is I'm going to tell you that I can do similar integrals with bosons where I only have one eigenvalue and I don't have the whole U going along. So let me give you a generalization. So I said I could introduce fermions, I could introduce these U bosons, and I could in principle do also something like a Gaussian integral if you wanted, the x exponential to something that would be inside here, where I take one of these eigenvalues and think of it as doing an integral of xi dagger times a dagger times x. And this is a Gaussian integral, and this is badly divergent. Okay. If you do this as an example and with some parameter, these behave very badly. Okay. You can do Gaussian integrals. There's a lot of ways to do it. But there's a way to do this which involves eigenvalues. So you can add a parameter lambda. You can put x over here. And then the problem of doing the Gaussian integral is that even though it's technically a generating function, it's not a nice generating function. It creates non-normalizable states. And part of the problem is also because the generators of a dagger, they kind of go unbounded. So that's what's going to be causing trouble. So what you can do is you can add a constraint that says that x dagger is equal to 1, for example. Okay. This constraint can be written in terms of an additional angular integral exponential of the x dagger, a dagger, lambda x minus x dagger x minus 1 times I theta. That's how you represent the delta function. And then you can really make a Gaussian. And you can show that with this constraint, this is also a coherent state with eigenvalues lambda giving the correct calculation because of that delta function. So these are also coherent states, and you can generalize these to not just x being a single column vector. You can have many columns, and you can have lambda, have different eigenvalues. And then this is when you take the number of matrices over here to be equal to n, to be an n squared matrix, this integral and this integral is the same. There's a way to write this U integral as some integral with an auxiliary parameter that enforces U dagger equal to 1. So in matrix integrals, all of these show up. So this is a slight generalization of this integral over here. And after doing all the contractions the way we've been doing so far, and gauge fixing, it has the same property that you can kill one of the U integrals or one of the X integrals by being careful. This has UN invariance also, and you can use that to basically gauge fix and get rid of one of them. So the answer will be something that looks roughly the same, where you get kind of lambda bar over here, something like this. And this integral with these constraints also happens to be soluble by localization. And because now lambda is not an n by matrix, but an n by k matrix, a k by k matrix, I can deal with one eigenvalue at a time. And then this prescription that I have with the vectors also works here. And I can deal with one d-brane in the bulk as opposed to having to keep track of n of them. So there's a way to eliminate, to pick out one eigenvalue by doing an integral, not over the full UN, but over something that's smaller. And then this object over here can also be done by localization, give you a similar integral. And you can also do the x integral first and write it as a contour integral in the complex plane and go to town with that and have fun with these calculations. And that gives you a very good idea of when the saddle really dominates and when you can kind of get rid of all the saddles and when perturbation theory works out. And then that lets you do calculations, again, of anomalous dimensions that will depend on these parameters in a particular way. So the goal right now is that we have this gadget that we just came up with. My students generalize these to SOSP. There's a similar integral over here that you can do with SOSP. The lambda and has to be the algebra valued, and then you have to go to some principal eigenvalue like the composition of lambda, and then the Harish-Chandra integral for these other gadgets are also known. And that gives you character expansions. And if you know something about SO to N, you know that there's a Pfaffian state. Pfaffian state is the determinant of Z. Not determinant, epsilon mu I2K, Z, I1, I2, 2K minus 1, Z, okay. This gadget shows up in there, and this is a brane wrapped on a non-contractible cycle. So these gadgets show up, and they show up in this expansion. So when I said that this knows everything, including these topologically non-trivial states. Again, the goal right now that we have is to try to understand these integrals a little bit better because they seem to give a handle on joining and splitting of strings in a really systematic way as opposed to what I would call the competition. It's a friendly competition. So the combinatorial methods were developed jointly. The modern combinatorial methods were developed jointly by Sanjay Rangulam and Robert de Mello Koch and various other collaborators. And it's been, like 50 papers. And even though, let's say, I've read a whole bunch of them, they're really hard to read and to understand. The combinatorial route is really, really hard. I just told you that I can do some of the combinatorics by integrals and pick saddles. These saddles are of order e to the n, right? When you do the computations of the right values, these are of order e to the n. So the corrections are of order e to the minus n. So if you're doing perturbative physics, you really don't care about this. So you really can throw away these other saddles. And then these give you a really, really good, nice handle on the calculation because the exact calculation has all of these non-perturbative effects in it, which are irrelevant for the problem of splitting and joining when it's trying to do with planar diagrams. So the advantage is that at the expense of not doing the exact answer, we get a huge advantage at the computational level that dispenses with these very, very hard combinatorial methods. I think it's a good place to stop. I'll let you ask questions and I'll dream of stuff to do.
Thank you for the talk. Are there more questions?
I didn't understand how the square n fits into your.
Okay. I think I can do that calculation. Okay, so let me start with this integral of the fermions over a vector. And then I have e to the I psi bar, and then there's going to be also, actually, no, this, well, yeah. Psi tilde, and psi bar tilde. Then I have plus I psi. There's no ice. And then there were these parameters, comi lambda, lambda star, and then I had the sigma. I think there was facts of I. And then this matrix is lambda, lambda star, and then it can be I sigma bar. Okay. And then you do this and you get lambda, lambda star plus sigma, sigma star, sigma bar to the n, eta minus sigma, sigma bar. This is what I was getting. And then you can try to do the saddle point calculation of here. And what you find is that lambda, lambda star plus sigma, sigma bar. And then I get to the n minus the log minus sigma, sigma bar. And then I need to take the critical point. Let's call this R and let's call this R. When you do the computation, what you find is that n over lambda, lambda star plus R is equal to 1. So R is equal to n minus lambda, lambda star. Okay. So the sigma is of order square root of n. And the sigma, if you do the saddle on the top, if you do the saddling here, what you find is that sigma is the expectation value of psi tilde psi bar or something like this. And you see that you pick up a factor of square root of n with a sigma. And then the point is that when you do the calculation of the anomalous dimension, you can bring in the original action, you bring 2 powers of psi and psi tilde, and then there will be some boundary contribution, and this power will give you EM squared, and then here you get a square root of n, and that's the thing that actually is the correct thing, because the words also have a non-trivial norm, and the square roots of n that show up in there also. So there's some combinatorics that goes in there, but the idea is that the sigma eigenvalue or the sigma parameter is not of order 1, it's a big of order square root of n. So when you start getting certain Tholen bilinears, you actually get factors of n or square root of n. This is really what's going on. That it's that combinatorics that's generating the extra factors of n. No, it has an n. This is the n counting. This is about n counting, not about dm squared.
So there's a gn squared from there, and there's an n from here. That's what gives you a total.
dm squared was there anyway because it came.
Yes. So if you do something that involves both boundaries, you bring something from the out and something from the in, and then each one of them will have a factor of this, and then that will give you sigma, sigma bar, or something like that, and then you get n. So, or you can have something where you bring one of these from the top and you have a different word on the other one, and one of the words will be a little bit longer, and that also carries an extra square root of n, and then these two things give you something where one square root of n plus the other square root of n add together to a EM squared times n in the normal. Yes. All right. So the dilatation operator has 2 lowering operators. So you're always bringing stuff. There's stuff that's kind of in the spin chain and it's the same as before. And then there's additional contributions that come from the dilatation operator acting on these exponentials that bring down the powers of a dagger, right? That bring whatever you have here, be they fermions or bosons or whatever. So every time you act to higher the border, you can end up also bringing some stuff from here. No. The point is that the powers of Yang-Mills come from the dilatation operator, but these bring stuff from the numerator And that brings powers of the fermions, and the fermions bring extra powers of n that compensate for things that would look like they're non-planar. So the idea is that I told you there was a saddle. There's perturbation theory on the saddle. And there's non-planar contractions of the psi's. And these non-planar contractions are not controlled by sigma. They're suppressed in 1/n, and then those give extra 1/n corrections that will correspond to splitting and joining and other stuff like that. Planar corrections to higher order in the G square times in the two-flapping. Yes, in principle, they're hard, but not impossible. I mean, one loop order, you get G squared Yang times n, and you get the usual spin chain on the word, plus some extra boundary contributions, because that's exactly when you can sometimes factor out a sigma or a sigma bar in the expectation values. But this is the expectation value. There's also a part that's kind of fluctuating, and these extra fluctuations will give you corrections that are non-planar. I might not be explaining myself carefully. So.
You use the three big contractions for A and A dagger to arrive at something like this. But when you go to higher order, then you don't need to use the fact that A dagger will also have corrections. Yeah, there are three, but I think when you're computing non-BPS correlators, I think for BPS correlators, yes, they are free, but for non-BPS, I think you will probably need to use them.
Yeah, but you can say, okay, what kind of non-BPS correlator do I get over here? If I pick my word carefully, I'm going to end up in one of these, for example, plane waves on the world volume of the giant graviton or something like that. Or I can end up with something, I end up with a spin chain. The ground state is going to be a lot better behaved. You can say something about, at least in the one loop spin chain, we know how to deal with the ground state of that one. And there's an R charge also that the word carries, and the corrections will be suppressed in the total length of that word, which is the R charge of that word. And then you can play these things against each other and find limits, like the plane wave limit or something like that, but you can compare. The sigma model with generic boundary conditions that we get here doesn't seem to be integral. But we seem to control the ground state. The ground state seems to be BPS with respect to some central extension, some other stuff. What I'm telling you here is the map to try to understand a little better splitting and joining of strings and trying to take that over. Because we think we know how to take states. At worst, is this kind of interval spin chain complication, whatever that does. But there's also a problem that we want to have we don't want to have a free theory of open strings. We want to see them interacting. So the question is, how do we get at that? And this is the stuff that the previous methods we weren't able to do. And this way, we seem to be able to do it. Because what will happen is that one of these lowering operators, for example, will act inside the word, and the other one will bring this stuff over here, and that will split the string into two. And that splitting and joining beforehand was really, really hard to do, and now I think we have a chance to do it. There's other things that these gadgets can do for us, because they can be computed by localization. I think Rajesh or someone else was mentioning this, exact computations that people try to do in n equal to 2 Yang-Mills that are valid for couplings. This gives a new hand on some of those as well, because this can be used to generate some interesting states that have the right supersymmetries. And then in those, also the problem of computing these 3-point functions or some nasty stuff will be reduced to correlators of, the integrals. But it's not clear in that case that there's a dominant saddle, so you might need to keep everything. And then what I found in the literature so far about correlators of U's in these type of ensembles is in the work of what's his name? Samson Shastadili. So Samson Shastadili studied some correlation functions that show up from these U integrals. And then the people who do matrix models like Einard and company improved on some of that. And then they can do maybe 2 U's or 3 U's. There's some recursion that shows up. It's really, really horrible the way it's written down. If sometimes you can reduce it to saddle, it's a lot simpler because it's just free weak contractions. But the stuff out there if one needs it. So the punchline in the end is that, this new gadget with these collective coordinates. I can also do quarter BPS states. This is interesting. Instead of having one lambda dagger, use a second one. And then you want to at least make the one loop anomalous dimension vanish. So you require the 2 matrices to commute. And then if you do that, the one loop anomalous dimension will automatically vanish in this stuff. So you can also do this with quarter BPS states. And this is something where having a nice generating function of certain quarter BPS states wasn't available before, and now we can have it. So, but the calculations, they're not soluble by localization. The saddles, but there's all the saddles that I don't control, and I cannot guarantee that they're exact. But in principle, I can do more complicated stuff, which is not just have BPS states, but 1/4 or maybe even 1/8. Okay, thank you.